Hello class. Today I want to develop a video on osmosis. Osmosis is really important, especially those of you in the allied health field. This is how cells accept nutrients through the cell membrane and also discard waste through the cell membrane. And you probably have seen examples of osmosis. If you take a cucumber and you place it into a salt solution called a brine solution, you'll notice that over time that cucumber will shrink and it becomes wrinkled, and we call that a pickle. And so what has happened there is you've got a solute, sodium chloride, outside of the cucumber, and the concentration of the sodium chloride is greater than what's inside the cucumber cells. And so the water will migrate from the cells of the cucumber to the sodium chloride solution, and that causes shrinkage, and we see that as the wrinkled pickle at the end. So what is osmosis? How does it work? And why is it so important? Again, it is our transport of waste and fuel for the cell. So I think one thing that makes students kind of not real sure about osmosis is, first of all, they can't quite picture that, and they always show a diagram kind of like what you see here, and you go, well, that doesn't look like that doesn't look like a cell to me, so what's going on? Well, the dialysis bag is the membrane. All right, so think of this being the cell, and then this is the boundary, the dialysis bag, between what's inside the cell and what's outside the cell. So think of it that way. And this dialysis bag is called a semi-permeable membrane. All right, so they have it here. What does that mean? It allows very small things to go through it. It does not allow large things to go through it. So water can flow between these. These represent water molecules, the blue dots, and then your solutes represented by the red dots. So water can flow through the semi-permeable membrane, but the solute cannot flow through the membrane. So what happens here is water will move through the semi-permeable membrane, trying to dilute the solution inside of the semi-permeable membrane. And so water will flow as pure water or solvent on the outside. It flows through the membrane trying to dilute the solution. You go, what does it mean to be dilute? Well, remember, that's a definition that we've talked about. Dilute is less solute per given amount of solvent. So the more solvent we have, remember the solute's fixed, there's only 5 of them, that stays fixed, and the water flowing into the semi-permeable membrane causes the overall concentration of this solution to be less. Now, this will keep happening until the pressure that's created by, if you look really closely here, here's the water line here, the solution line, and then here it is, here it's moved up. That difference in the water line is the pressure. Remember, pressure, this is all starting to come together. That's why I say, Chem 140, if you don't get the first 4 chapters, it all falls apart, because we've already talked about pressure actually in chapter 5, and pressure is force per area, and you've got an area here, and there's a force, there's a gravitational force pushing down, or pulling downwards on the mass here. So we have a pressure, and so when we move from this where the solution is to up here, that creates a difference in pressure. And so once the pressure gets so great, the solvent will stop flowing through the membrane. So that's actually what osmotic pressure is. If we determine the amount of mass we have here, and we determine the force pulling on that, we can determine the pressure, and that pressure is called osmotic pressure. Now, what you can do is, let's say you start here at the beginning and you don't want any of the solvent to flow into the membrane. You could apply a pressure down this membrane like so, and you could stop the flow of the solvent through the semi-permeable membrane, in this case water. So osmotic pressure is super important, and so I think why people have problems with osmotic pressure is it does pull in a lot of the information that we've already talked about. So like here we've defined what pressure is in a previous chapter, chapter 5. We have talked about concentration, and we've talked about dilute and then also concentrated solutions. And so concentration, the most common unit we use is molarity in chemistry. So molarity, you have to remember that, which is moles per liter. And then here's the hardest part, I think, with concentration. You have to know whether the solute is ionic or covalent. And that's probably where students get tripped up the most, because what we're talking about in osmosis is colligative property. So if you don't know what a colligative property is, you want to go back and read that section carefully. But a colligative property is not a chemical property. It is a property dependent upon the amount of solute molecules or particles dissolved in solution. And so we've talked about freezing point depression. That's why when you throw salt out onto the sidewalk, it will melt the ice. It lowers the freezing point. If you are really observant, you can put a thermometer in some boiling water and add some salt to the boiling water, and you'll actually see the temperature of the water go up. And that's called boiling point elevation. So we talked about freezing point depression, boiling point elevation. Vapor pressure is another one. When you add a non-volatile solute to a volatile solvent, such as alcohol, it lowers the pressure that is exhibited by the solvent in a closed system. And that's where we get equilibrium. When there's an equilibrium between the liquid solvent and the gaseous solvent, we call that vapor pressure. So out of all of those, probably osmosis is most important for those of you in the allied health field. So the other thing that you need to remember about osmotic pressure is, where does pressure come from? Well, again, chapter 5, we saw the ideal gas equation, PV equals nRT. And you go, well, that doesn't look like the osmotic pressure equation I saw in the book. Well, if we divide both sides by V, we get P equals N over V RT. And then you can recognize that N over V is the same thing as molarity. So this equation then transforms to pi representing osmotic pressure equals the molarity times RT. So some people get all confused about this equation. It's really the ideal gas equation, all right? They're not different, really. It's the same thing. So if you get stuck and don't remember this equation on exam, just write this equation, and then you know what the moles and volume are, and you can figure out what the osmotic pressure is. All right? So again, osmotic pressure, it's the amount of pressure that has to be applied to stop the flow of the solvent through the semi-permeable membrane. And the key to remember is the solvent will flow from the dilute solution to the more concentrated solution. All right. So osmolarity. So this is the first thing that trips up students. And so you hear the word molarity and you go, oh yeah, I know molarity. Molarity is equal to, we just saw it, molarity is equal to moles divided by volume. So everybody's got that down. I don't find students really miss that part. But this isn't just molarity, it's osmolarity. There's an I here. So what is I? I is the number of moles of particles or moles of solute. Okay? And then the M is, the molarity, you already know that. So this is what I'm getting at here. You could have a 1 molar solution of sodium chloride. And here's where most students make the mistake. Not so much on this one, but if I threw up another one. So what happens here is you go, oh, sodium chloride. Well, the first thing you have to do when you look at that substance, you have to know, is this ionic or covalent? So we spent all this time, chapters 1 through 4, defining what's ionic, what's covalent, did Lewis structures and all of that, what are the ion charges and so forth. So here's where you're going to use this in real world. So you got sodium, which is a metal, and you got chlorine, which is a nonmetal. So you know this is an ionic substance. You know that when you add sodium chloride to water, what you actually get is a sodium ion, and you get a chloride ion. And if we want to be complete, we'd say aqueous. It's not drawing it. Aqueous and aqueous. And it's not. This little Wacom board's not quite doing it for me today. All right. So ionic substances, you know the solubility rules. If you haven't memorized the solubility rules in the previous chapter, you need to do that, because this is where this gets to be really important. So sodium chloride, you know, dissolves in water according to the solubility rules, and it forms a sodium ion and a chloride ion. So for every 1 sodium chloride formula unit, we actually get 2 ions. So that's what this I is. I says, okay, for every one of these sodium chlorides, we get 2 ions. So the total osmolarity for sodium chloride would be 2 molar. All right, that would be the osmolarity. So you multiply the number of ions formed times the concentration, and you get the osmolarity. So what does that mean? You have to look at the substance critically and determine if it's ionic or covalent. Because let's say it's something like sugar, C6H12O6. So if you look at that, you would say, oh, well, this is not ionic. This is a covalent substance. And when I put sugar in water, it doesn't break apart. It stays intact as a molecule of sugar. So if the concentration of the sugar is 1 molar, the osmolarity is going to be 1 molar, because sugar doesn't dissociate into multiple ions. And that's where students really miss it. They don't take the time to evaluate the substance and determine if it's ionic or covalent. And then the other thing, if they're still kind of sketchy on what are the charges on the ions, especially the polyatomic ions, they don't know how many particles it breaks into. So like, here's a good example. Let's say I have 1 molar sodium phosphate. Can you write the chemical formula for sodium phosphate? Try it. Stop the video and see if you can write the chemical formula for sodium phosphate. Okay, so what it should look like is Na subscript 3 PO4. If you didn't get this right, that means you got to go back and look at your naming and your really the naming and then the ionic charges and so forth. So this polyatomic ion is a -3 ion, and that's why you need 3 +1 sodiums to make that a neutral compound. So if you're not getting this right, you don't have any shot at osmolarity, because what you would see then is, oh, sodium phosphate. When I put this in, does this dissolve in water? That's the next question. Does this dissolve in water? And you would go, yeah, also group 1 ionic compounds dissolve in water. And what you get then is 3 sodium ions. And then you have to recognize that phosphate is a polyatomic ion PO4 with a -3 charge. So the total number of ions generated here is 4. So that's what I is. I tells you how many particles are dissolved. So we would take 4 times 1. So the osmolarity of the sodium phosphate would be 4 molar. All right. So think about what we've talked about here and decide what your weakness is. Is it you don't know the charges, you don't know the names, you don't know if it's ionic or covalent? All of these things play in to getting this problem right. So the other thing you notice, I didn't put the I in, and I should have. I just think of the M as the osmolarity, how many particles I have. But they actually say IMRT, and the I represents how many particles do you have. So either way, just make sure you know how many particles is it. Remember, colligative properties is the number of particles dissolved in the solution. Don't forget that you know what R is, 0.8, 0.08206. So, I mean, you've done that. Or 0.0821 liter atmospheres mole Kelvin. You know the temperature has to be in Kelvin there. All right, so this is like a problem in your homework. And actually, yeah, I chose the same thing. It's that common, right? So we want to calculate not just the molarity, we want the osmolarity of this sodium phosphate solution. So here's the molarity. Again, look at the substance. It's ionic because it's a metal with a polyatomic ion. Does it dissolve in water? Absolutely. All group 1A compounds or group 1 metal ion compounds dissolve in water. So here we have it. It dissolves into 4 particles, right? And so they have 5 times 10 to the negative 3 moles per, this is a typo here. Yeah, that's a typo. It should be liters. That's pretty bad. All right, and then you would say 5 times 4, and that would give you 20 times 10 to the negative 3, but when we make it in scientific notation, see again, that's why you have to know the chapters 1 through 4 to be successful. To put that in scientific notation, it's a digit, the decimal, the rest is significant figures. That becomes 2.0 times 10 to the negative 2 mole particles per liter. All right? So think about where you're making a mistake. Do you know this is ionic? Do you know what the formula is? In this case, they give it to you. Do you know that that stays intact as one polyatomic ion? If you don't, that's a problem. Because then if you said the phosphorus and oxygen break apart into multiple particles, you could get like 4 oxygen, 1 phosphorus, and then 3 sodium, and you'd have like what, 8 particles, and this would be an 8 down here, and you'd have an osmolarity that's double what this is. So that's what you got to watch about. Well, it'd actually be 8. It'd be even double. Okay. So that's the first part. You got to calculate the osmolarity correctly. If you don't get this part, the rest of it doesn't make sense. Well, let's move on. All right. So you go, why do I need to know this stuff again? This is what determines what type of IV you're going to give a patient. Are you going to give a patient an isotonic solution, which has the same osmotic pressure inside and outside the cell? You're going to give them a hypertonic solution, which the concentration is greater, it pulls stuff out of the cell. You're going to give them a hypotonic solution, which actually puts fluid into the cell. So this stuff will be determined, but if you understand where it comes from, you can always double check. Somebody gives you the wrong bag of solution, you're going to be saying, are we trying to put the medicine in or take the waste out? What are we trying to do here? We're just trying to keep the fluid up. This is the kind of stuff that's really important. And I know you don't think about it every day in the hospital, but it's just something that if you understand it, you have a better idea of what's going on. All right, so this question says, calculate the osmotic pressure of 5.0 times 10 to the negative 2 molar solution of sodium chloride. So first thing that you want to do, as soon as they say osmotic pressure, you want to write down the equation for that. Pi equals IMRT. And then you start filling in what you know. Well, the first thing you have to do is, let's figure out what I is. Well, you look at sodium chloride and you go, oh yeah, that's an ionic compound. I know that one for sure. And you know that sodium chloride, when added to water, dissociates into a sodium ion and a chloride ion. So it dissociates into 2 particles. All right. So that's what I is. I is 2. And then you have the molarity. And so that's what we have here. The 2 particles. We have the molarity. We have, I said 0.08206. They rounded to 0.0821. That's fine for either one. In fact, that's fine because this is only down to 2 significant figures. Concentration. Now, I can't stress enough in this class, write your units down. Watch the units. Watch the units and it'll guide you to the right answer. Watch this. This mole and that mole cancel out. That mole and that mole cancel out. That liters and that liters cancel out. and that Kelvin and that Kelvin cancel out, and you're left with atmospheres, which is a pressure unit. So take the time to write your workout, watch your units, and a lot of times you'll get the correct answer if you just do that, all right? So if I don't want the liquid, the solvent, to flow into the solution, then I need to apply a pressure of 2.4 atmospheres, and that will push the solvent, keep the solvent from flowing through the membrane. That's why it's important. So I don't think it's this. I don't really think it's this that's giving students the most problem. That's not too hard to memorize. I really think it's you've got to evaluate this, and if you're not getting that correctly, then it causes big problems. And you got to go back to those previous chapters. And if you need help on that, I would say use the Thinking Storm online tutoring. Get somebody you can dialogue with and talk about it. But that's why the first 4 chapters are critical. That's why I make that at midterm you have to decide whether you're going to stay with the class or withdraw. Because I generally find students who fail the midterm miserably, they can't make it through. They cannot make it through the class. And they have to retake it or something like that. All right, let's go to the next slide. The next slide is a blank, and the reason why is I thought we'd do another problem. Let me just do one real quick. Let's say you have a 2 molar methane solution. And it's at 25 degrees Celsius. And I want to know what the osmotic pressure is. All right? So the first thing you have to do is, okay, osmotic pressure, again, pi equals I, if you want to put that in there, MRT. All right? The next thing you have to do is you have to determine, is methane an ionic compound or a covalent compound? And you would say, oh, it's covalent. And so it doesn't dissociate into a carbon and a bunch of hydrogen ions or something like that. It stays intact. It stays together. Now, technically, I don't think that methane's not going to really dissolve in water at that concentration, but for the sakes of this problem, we'll do it. But you're not really going to see a 2 molar methane solution in water at 25 degrees Celsius and 1 atmosphere pressure. But anyways, it'll still work. I'm just saying it's kind of a ridiculous solution concentration. All right, so here's what we have. You know methane stays intact, so I is 1. Because it's not ionic, it doesn't break apart into ions. You know that for every one of these methanes I have, it stays intact. So if I have 2 moles of methane in a liter solution, I'm going to have 2 moles of methane particles in a liter solution. So pi equals I is 1, nothing breaks apart, times the molarity, which is given, 2 molar, times our 0.0821 liter atmospheres mole Kelvin. And then the temperature, notice this is in degrees Celsius, and I see students do this all the time. They don't convert that to Kelvin. So you got to add 298 to that, or 273 to that, and that gives you 298 Kelvin. That's a common mistake. Now, here's how you catch the mistake. If you will write your units down, molarity is moles per liter, and you got liters per mole here, so that cancels out with that. And then this Kelvin cancels out with that. And if you had this as 25 degrees Celsius, you would see they don't cancel out, and you wouldn't get atmospheres by itself. That's why it's important to write the problem out on your scratch paper and make sure that you're getting the correct units. All right, so get your calculator. Let's calculate this out. 2 times 0.0821 times 298. Oops. And I get 48.9. We only have, what, one significant figure. So here's another thing. So here's my rough answer. 48.9 atmospheres But I only have one significant figure here. So what's this to one significant figure? You just write 50 atmospheres. 50 is one significant figure. Or if you want to make sure it's not ambiguous, you would write 5.0 times 10 to the first atmospheres. Okay. Well, I hope that helps. Osmotic pressure, very important. It's time to master it now, especially if you're in the allied health, because you're going to hear osmotic pressure a lot in your biology classes. It's that important. And I just find students that are in biology that haven't had osmotic pressure, they really struggle. They don't understand it. And part of it is biologists are going to focus on that transport through the membrane more than the pressure maybe, or they're going to focus less on that what does the substance dissociate into, and that throws off students. Because I mean, truthfully, you have to understand whether the substance is ionic or covalent in order to do this problem. And if that's a chemistry thing, that's not really the biology part. So make sure you know if it's ionic or covalent. Make sure you know how, if it dissolves in water caused by the, go back and refresh your memory of the solubility rules, and then know what it dissociates into. Is it 3 sodium ions and a phosphate? Again, that means you need to know your polyatomic ions and the charge on them. Hope this helps, and if you need additional help, just email me. I'm here to help you, and this is the way we're teaching now. So good luck, and again, email me if you need help.